Well, hello again, and welcome to presentation number 3, Leveraging Common Data Models for Multi-Jurisdictional Research. This presentation provides an overview of the types and characteristics of common data models, examples of Canadian studies undertaken with common data models, and highlights new statistical methods for analysis of observational data that were developed using a CDM. I'm going to take a moment to quickly introduce the panel. Just a reminder that their full bios are available to you on the platform, and we won't read out their full bios here. So our first presenter is Dr. Robert Platt, who's a professor at McGill University. Next, we'll have Mike Patterson, Senior Scientist, Research Program Lead and Science Advisor at ICS, followed by Mahmoud Azameh, Director of Data Quality and Information Management at ICS. And then Dr. Therese Stuckel, Senior Core Scientist in the Primary Care and Health Systems Research Program at ICS. Remember to put your questions in the chat in the Q&A tab, and that way we will do our best to ask as many of your questions as possible. But now, without further ado, I'll turn things over to Robert Platt.
Thanks, Michael. If we can have the slides. Perfect, thank you. So I'm going to just introduce the concept of a common data model in a general setting, and then the others are going to get into some of the details and some of the examples we're going to talk about today. So if I could have the next slide. Thank you. So this is an outline. As Mike has already introduced, we're going to give the general introduction and then some specifics looking at both Canadian and other uses of common data models. Thanks. If I could have the next slide. Next slide, please. So I'm going to talk briefly about federated analysis, and this is one of the primary reasons we need common data models. In Canada, I work with CNODES, the Canadian Network for Drug Effect Studies. We work using the provincial databases across the country. It's typically not feasible to pool the data sets from the provincial administrative data across the country. So we work in a federated environment. And there are many ways we can do this. We could do separate analyses in each province and then pool the results. We could use common protocol-based analyses where we write a common protocol and then share that across the country. We could use a common data model, which is what we're going to talk about today, which brings some efficiency over the other two approaches. And then we could talk about fully privacy-preserving, fully federated analyses like Data Shield is one Canadian example of that. If I could have the next slide, please. So the two I'm going to focus on today are the idea of the common protocol versus the common data model. And common protocol is the way that CNODES has worked for many years. Common data model is one that we've taken on in the last several years as an alternative to that. In the common protocol setting, someone in a centralized site writes a protocol and a statistical analysis plan that's distributed to analysts in the different sites. The analysts run that analysis plan on their own data, customizing the code as needed to make that work, and then return summary results to the central site who produces a report. In the common data model setting, this is a schematic on the right of how this works. Rather than sending an analysis plan, because the data are standardized across the sites, and we'll talk about what this means and show some examples over the course of the morning. Because the data are standardized into this common format, we can just send code from the central site to the individual sites, and then they will just automatically run that code against their data and return the results to the center. If I could have the next slide, please. So let's take a step back and talk briefly about what a common data model is. And it's not actually a single concept. I'm going to describe a few different ways that it can be used, and the others are going to talk about specific examples of different ways that these are put into practice. But a common data model is a tool to standardize data into a common format, which can mean structure, that is the same basic data set formatting of the same columns, meaning roughly the same things. It could be formatting where we structure our variables more into, say, different value sets or different coding systems. And it could mean standardizing meaning in terms of encounters and so on. And a common data model, and we'll see examples of this in later slides, may include the analytic code and analytics layer that I described in sort of the schematic on the last slide. Next slide. So I mentioned the common protocol approach earlier. Just briefly, some advantages and disadvantages of it. It does give analytical flexibility. That is, the design, the data sources, and the statistical methods can be tailored to the local data. So if you have heterogeneous data across the different sites of your federated network, you can flexibly tailor what you're doing to the sites. It also allows for local capacity building. It builds analytical skills, methods expertise, and data repository development in the individual sites. On the other hand, this takes longer to do because the coding is being done separately at each of the sites. And there's risks for inefficiency and error because the coding is being done individually at each of the sites, and there's errors could creep into the individual data analyses. Have the next slide, please. So why a common data model? Well, a common data model is an alternative to that, where if the data are standardized, we can run standardized code against those data. We can build, say, a single program to conduct a regression analysis, and we know that that will run against all the data sets in the system because the data sets all have the same format. This code is therefore more reliable. It's been tested against this data format. It's reproducible because it's been tested. It's rapid because we don't have to write separate code to run a regression. It's just there. It provides guardrails because it restricts the analyses that you can do. So in some sense, it prevents inappropriate analyses. And at the extreme, it produces standardized or automated reports, and where we can just say, I would like a report on the use of drug X in population Y in the Canadian provinces over this time window, and a fully formatted report can be produced based on that. In multi-jurisdictional studies like CNODE's studies, we know we're running the same codes across multiple sites, so that improves our quality control as well. Next slide, please. So now I want to break down a couple of different types of common data models, and you're going to see both of these examples throughout the day. So I'm going to talk about an organizing CDM, and the Sentinel that Mike Patterson is going to talk about is an example of an organizing CDM. Essentially, an organizing CDM just reorganizes the data files into a standard data structure, and it doesn't modify the raw data content in any way. So if you have a diagnosis database, it just reorganizes it into ID, date, diagnostic code. It doesn't change the diagnostic codes in the system at all. And this then requires project-specific coding because you have to build your diagnostic definitions on a project-by-project basis. We refer to this as an adaptive rules system. The OMOP or Odyssey common data model is what we call a mapping common data model, where the raw data are mapped to either what are sometimes called concepts or constructs. So rather than leaving the raw diagnostic codes in a database, we might ask for, or we might define incident type 2 diabetes as a certain set of codes occurring in a certain pattern in a certain time window. The mapping can be comprehensive, that is, you map your entire database, or it could be study specific. We'll talk over the course of the morning a little bit about how this mapping actually happens. But it's obviously one of the most important steps in conducting analyses with a common data model like this, to make sure that your concepts are well defined and correspond with the right things in your raw data system. And this we'll refer to as a pre-configured rules system. Next slide, please. So this is just a brief schematic of this, of the common data model structure. So we think about the raw data in the bottom slice of this graph. That's just our ordinary relational database, data warehouse that contains all of our data files. The next layer up is this idea of an organizing common data model, where we just might standardize things into similar formats without touching the data, so that a data file capturing encounters looks exactly the same in one system versus another. It doesn't have the same codes necessarily in it, but the format of the data in terms of the rows and columns looks the same. We could then take an organizing common data model like the FDI Sentinel, for example, and either go directly to programming it. That's the sort of burgundy box on the right. We could use adaptive rules, and Mike Patterson will talk about this later. Pre-programmed sets of analyses that will run standardized analyses. Or we could go the next step and convert the data into a mapping common data model like OMOP. And then that could run these fully pre-configured rule systems, which are essentially fully automated analyses. Or it could do the other two approaches. But the important part of this graph is the idea that the data sort of get more and more tightly structured the further way up you go. And you have choices in the top part about how you deal with your variable definitions and then your analytics, your data analyses. Next slide, please. So these are some broad examples, and I'm just going to illustrate a couple of the others that we're not going to talk about in particular. The other speakers are going to talk about the Sentinel Common Data Model and the OMOP Odyssey Common Data Model. But there are others. The Conception Project is an international common data model focused on pregnancy and mother-baby linkage studies. So they've put a lot of effort into the specifics of those problems. PICORNet is an open research common data model, primarily in the US. And then there are a number of commercial common data models. Adion, Panalgo, and Trinetics are all examples of commercial systems that overlay on the raw data to produce automated analyses in a way that's somewhat similar to the ones you're going to hear about later today. Next slide, please. And with that, I will turn it over to Mike Patterson, who will talk about our work at CNODES with the FDA Sentinel Common Data Model.
Thank you very much, Robert. Next slide, please. So for those of you, excuse me, who aren't familiar with CNODES, we are the Canadian Network for Observational Drug Effect Studies. And the network is comprised of essentially a national distributed team of pharmacoepidemiologists who have access to provincial administrative health data. We're currently funded by CADTH, the Canadian Agency for Drugs and Technologies in Health, that was actually yesterday renamed Canada's Drug Agency. And our aim is really to provide timely responses to drug safety and effectiveness research questions that come to us from a range of Canadian public stakeholders, primarily the Health Canada regulatory branch, but also the provincial drug programs, and others like the Public Health Agency of Canada. Next slide, please. So this just gives a schematic of the provinces that are currently represented in CNODES. In addition to the provincial data sets, we also have access to the UK CPRD, that's the Clinical Practice Data Link, EMR-based, primary care EMR-based data set from the UK, and private insurance data set called US Market Scan. Collectively, we have within these data sets approximately, over 100 million individuals. And I think that one of the key advantages of having a distributed network like this is that we're able to generate much more precise effect estimates by pooling the results across these sites than any individual site could generate. Next slide, please. So when we talk about the linked provincial administrative health data, we're really talking primarily about the data sets listed on the left-hand side here. So these would be the provincial health insurance registries in Ontario. That would be the OHIP registered persons database, our provincial drug claims, physician service claims, hospital discharge abstracts, emergency department records, vital statistics, same-day surgery records. Those would be our core administrative health data. And those are the data that we leveraged for our common data model work. On the right-hand side, we, on occasion, particularly in the protocol-based era, have involved a number of other data sources that you can see, like the provincial cancer registries and laboratory data for our COVID studies. But these are not integrated formally into our common data model tables, but are called upon from time to time, depending on the particular research question that's asked of us. Next slide, please. So as Robert said, we at CNODES decided to adopt the FDA Sentinel Common Data Model. And we did so for a number of reasons. The main ones would be that this particular model translates very quickly and easily to the health administrative data that we use. That's the primary source that's used by the FDA Sentinel system. Another reason would be that it's, as Robert said, fully transparent. All the codes essentially are as they were in the raw data files, so it's easy to trace back outcomes and cohort definitions. Another reason would be that Health Canada was eager to have us collaborate with FDA. And so we could certainly adapt the programs that the FDA had already developed for their own studies for use in Canada. And another reason related to that is the suite of query tools that I'll talk about in a minute. And these are the reusable, flexible, modular SaaS programs that Robert mentioned that essentially allow us to generate standardized output tables for a number of research questions that were common to us coming from Health Canada and the public drug plans. So I'll talk about the contents of the two main components, the standardized data tables and the query tools. And these tools will answer questions. I'll provide some examples in a minute. Things like the numbers of newly exposed individuals to specific drugs over specified time periods. Another looks at raw crude outcome event rates among new exposures to drug therapy. Others, more specific programs, look at concomitant drug use, persistence with drug use, switching, etc. Next slide, please. So this is just an overview of the common data model tables that the Sentinel Common Data Model include. In the upper left-hand corner are our core administrative data tables. The enrollment and demographic table draw primarily from the provincial registries. So our OHIP registered persons database, for example, and these tables contain information about insurance coverage and basic demographic characteristics. The dispensing table pulls from our provincial drug claim data in Ontario, Ontario Drug Benefit Plan data. And then we have encounter, diagnosis, and procedure table. And these tables draw from multiple underlying data sources. So these would be our physician service claims, our discharge abstracts, emergency department records. And all of these tables are linked, as you can see in the upper row, by a patient ID. So this is an encrypted version of our health insurance number, and that's used consistently across all of the provinces. And then for the encounter, diagnosis, and procedure table, these are linked by unique encounter IDs. So regardless of whether the encounter is in the outpatient setting or the inpatient setting, all of that information across the diagnosis and procedure codes can be linked by a unique encounter ID. In the lower left-hand corner is our death registry, which is obviously critical to track deaths that occur in our cohorts over time. And in the lower right-hand corner, we have the mother-infant linkage data table, which is important for studies of pregnancy drug exposures and outcomes. Next slide, please. So this is an image that depicts the Sentinel, FDA Sentinel query process that we've attempted to emulate in CNODES. In the first stage, the FDA query submitter would meet with members of the Sentinel Operations Center to essentially populate the SAS program for the query that's of interest. So they would work together to develop the input files that describe the study cohort that's of interest, the diagnosis and procedure codes for that, any of the comorbidities or covariates that would be included in the analysis, and then also, obviously, the drug information codes would have to be compiled as an input data file. Once all of those what we call specifications for the study have been determined, that SAS package would then be run on a standalone data set, typically the market scan data set I talked about earlier. And once the output tables that the query submitter is happy with are established, those SAS packages are then distributed to each of the data partners. In the Sentinel system, this would be 18 separate data partners. Here in CNODES, it would be the provincial data centers. And then those SAS programs are run against the standard data tables that we've established, created and QA'd at each of the sites. A standard output is generated at the sites. They're reviewed. Step 5, once cleared, they're returned to the coordinating center where established aggregation programs are run against the site level data to establish overall national tables. And then those are ultimately shared with the query submitter. Next slide, please. So as I said, I'm just going to give you a high-level overview of examples of some of the programs that the FDA Sentinel program have used to answer questions. All of this information, both the construction of the tables and all of their queries, programs underlying the SAS programs that have been populated for those, they're all available in the public domain on the Sentinel website. So these include, as I said earlier, concomitant drug use, characterization of patient cohorts and their drug use, crude outcome event rates, in this particular case, dabigatran and warfarin anticoagulants, and subsequent bleeding events. Next slide, please. More recently, the team has developed a series of SAS programs for comparative analysis, both propensity score matched cohort studies and weighted cohort studies. And this one here compared dabigatran with warfarin and gastrointestinal hemorrhage. It was the outcome. And then also some self-controlled risk interval analysis, which are are common in vaccine safety studies. Next slide, please. So early on in the life of CNODES, under our funding through CHR, we received some feedback from a formal evaluation of CNODES performance in the first phase. And one of the key criticisms was that we needed to do our work more quickly and more efficiently. We needed to implement systems that allowed us to provide more timely responses to the questions that were being asked of us. And so we decided that we would seek additional funding to establish, essentially transform our admin data into the FDA Sentinel Common Data Model. And we did this in 2 phases listed here. And we undertook a series of pilot studies to first demonstrate that we could use these tables successfully, but also to generate an estimate of the time savings that would be accrued by moving to a common data model. Next slide, please. So this just gives you a sense of the timelines for our initial pilot studies in the first phase of our Common Data Model pilot project. The column 1 here lists the timelines for the data custodial and RAB approvals at each of the sites, ranging from 5 days in Nova Scotia to 50 days on average in Manitoba. It took a couple of weeks typically once those approvals were obtained to run the SAS packages for each of the programs. And then step 3 would be seeking approval to share the small cell tables. Some of you will know that we're typically not able to share cells in tables less than 6. Varies a little bit from province to province, but that's our lowest common denominator. But for the purposes of pooling results across sites, we had to seek special permission in order to share those small cell tables so that they could be pooled at a national level. We weren't able to achieve that in Manitoba, so they in fact became our de facto pooling center. And we established protocols for that sharing at the other sites. And the time for obtaining approval for that varied from province to province. In Saskatchewan, that was our longest approval time during the pilot, which was 42 days on average. We've been able to bring that down considerably with experience to 1 to 2 weeks. Running the aggregation program in Manitoba takes just a few days. And so during the pilot project, we were able to achieve timelines in the range of 80 to 90 days, which is half, if not better than half, of what we would have achieved under a protocol-based regime. Next slide, please. Since our pilot projects, we've run a number of international collaborative studies with European teams and the FDA. They're listed here. The first was a request from Health Canada to study the impact of angiotensin receptor blocker recalls, nitrosamine contamination recalls that occurred in 2018. The second was the first of several studies in the COVID era. It looked at the utilization of corticosteroids for the treatment of mild COVID in the outpatient setting. And that was a collaboration with FDA and EMA, the European Medicines Agency. And then the last, more recent one was a study of the natural history of coagulopathy in patients with COVID, both in the outpatient setting and in the inpatient setting. And that was also a collaboration with FDA and EMA. Next slide, please. Just to give you a sample of the results of the last study, again, this study looked to assess the risk of arterial and venous thrombosis within 90 days of infection, both in the ambulatory setting and hospital setting. In Canada and US, we used the Sentinel Common Data Model. And in Europe, we used the OMOP Common Data Model that Mahmoud will be talking about in a minute. Next slide, please. This just gives a sample of one of the figures from that report. It's a monthly time series of the 90-day rate of these outcome events. The blue is the venous thrombotic events, red arterial thrombotic events. The upper left-hand corner is the results from Canada. The lower right-hand corner, the results from the United States. And then England, Germany, Italy, Netherlands, and Spain between them. As you can see here, a fair bit of heterogeneity across countries. Some of the lowest rates in Canada, some of the highest in the United States. Number of important messages flowing from this. In Europe, with the OMOP Common Data Model, it was actually the underlying data sources for the Common Data Model are a combination of administrative data and EMR data. So that certainly contributes to some of the heterogeneity that we see across the European centers. In Canada and the US, the underlying data sources for the identification of COVID in the first place differed. So in Canada, we used exclusively lab data to define COVID infections. In the United States, they used a combination of lab data and outpatient diagnosis codes, which we know from our validation work in Canada is less than ideal. Having said that, I think some of the key messages that flow from this are that the Common Data Model can help standardize the way in which we're undertaking our studies and make it more efficient. But the underlying data sources that are used to contribute to the Common Data Model files and how the cohorts are defined and outcomes defined obviously is critical. And we can't remove heterogeneity by simply adopting a Common Data Model. These other factors are very important. Next slide, please. So looking forward for CNODE's use of the Common Data Model, we obviously, as we saw earlier, one of the important bottlenecks in the process is the REB and data custodial approval times. In fact, they've gotten longer in some provinces rather than shorter since we adopted the Common Data Model. We have to continue to negotiate shorter approval times in order to get responses to our decision makers in a timely way, and we're looking at various options for doing that. We've yet to obtain data from Quebec in order to create Common Data Model tables. We're continuing to look at ways to do that. And then finally, recently, Sentinel has introduced a number of new SAS packages that we've yet to use. We're just now using some of the propensity score matched and weighted models, modules that they've developed. And then recently undertaken some new demonstration projects and using some of the latest modules they developed, things like tree scan, safety signal detection protocols that they use routinely in the US, and we're testing some of those in Canada as well. Next slide, please. With that, I'll turn it over to Mahmoud.
Thank you, Mike. In my presentation, I'm going to give you a brief overview of OMOP, a Common Data Model, and Odyssey, and then I will jump into a use case, which is a pilot project by HDRN Canada. Next slide, please. This is a representation of what is Common Data Model, and which I borrowed from Odyssey, and I thought this is a good way of representing what is a Common Data Model and how it can help. So here you can see different electric outlets in different countries, which represent data. So they are all different. And on the left, the iron is representing your analytic tools, and the plug is the application to the data. So obviously, it only plugs to one type of data, but not to others. Next slide, please. So what Common Data Model is to standardize your outlet. So all of the outlets in different countries will look like the same. And that enables you to plug your tools, your analytic tools, to all of them, which is here iron is representing your specific analytic tools. Next slide, please. So analytics in this setup can be remote. So data remain in the same where they are. Analytic can be somewhere else. You just extend the wire of the iron, and then still you can run the analysis wherever the data actually is hosted. Next slide. Analytics can be behind a firewall. So secure environment, we are all familiar with our secure environment. So analytic doesn't necessarily have to be within the secure environment. It can be outside of a firewall, and still common data models enables you to run your analysis. Next slide. And another application of a common data model is network studies or networks of networks. So you can have multiple networks that are on different setup or different within different firewalls or analytic secure analytic environment, but you will be able to connect these together through analytics running on common data models. So another advantage of having common data models. Next slide, please. OMOP stands for Observation on Medical Outcome Partnership. It was funded by FDA in 2008 for studying drug surveillance and adverse event detection. In 2014, OMOP left FDA and moved to Columbia and changed its name to Odyssey. The name OMOP is still being used, but they're sometimes being used interchangeably. Odyssey stands for Observation on Health, Data Science, and Informatics. Odyssey is currently hosted at Columbia University in New York. And usually Odyssey is often used to refer to the open science community that supports OMOP CDM. OMOP is fully open source, and data queries are posted in Odyssey GitHub for anyone who is interested to use. Next slide, please. Thanks. This is a map of collaborators that Odyssey has published. This is the most recent one. So Odyssey claims that there are 3,758 collaborators across the world in 83 countries, which are all belong to one community, which is the Odyssey community. Next slide, please. This map shows the common data model, OMOP common data model adaptation. Again, from Odyssey, it is claimed that there are 534 data sources already converted into OMOP common data model in 49 countries, which represent 956 million unique patient records. Next slide. This is the schematic diagram of OMOP Common Data Model version 5.4, which is the latest version that is supported and fully supported and published. As you see, it's I don't expect you to be able to read this, but this is just to give you a sense of the complexity of this relational database structure. OMOP is a highly normalized structure. And as you see, the more normalized you convert your data, it becomes more complicated. But of course, it gives you flexibilities to do more, as you will see in future. Next slide, please. So this slide, I'm trying to give you a sense of how standards and non-standard sources and classification concepts work in the OMOP common data model. As you see in the bottom, you can see different classification or coding system. For example, ICD-10, ICD-10-CM, SNOMED, Mesh, ICD-9CM, etc. They all need to be converted to SNOMED CT, which is considered the standard concept or standard coding classification for OMOP. So all of those needs to be converted to one standard coding. And in the next slide, you will see how, as an example, how the hierarchy of a condition works in SNOMED and in the common data OMOP common data model. This is an example of atrial fibrillation. So from top to down, it gets more granular code from, as you see, from the disease of a cardiovascular system, it goes to the heart disease, cardiovascular arrhythmia, and as you go further and further down, it will granular the data in a hierarchy structure, which leverages SNOMED CT. Next slide, please. Odyssey comes with a bunch of open source software tools. And in this slide, you can see a few of main tools that are available for Odyssey. On the left, you can see White Rabbit and Rabbit in Hat. These are two softwares that helps you to design your mapping conversion ETL. There is a data quality dashboard that helps you to assess once you create your OMOP common data model, to assess the data quality of that in a harmonized and standard way. Athena is an online resource that allows you to download and search standardized vocabularies. Usagi, which I recently learned in Japanese means rabbit, is a fuzzy matching software for code mapping. For example, when you want, in a Canadian context, if you want to convert ICD-10-CA to SNOMED CT, you load the description of both codes, and it using fuzzy matching, it suggests you the best match and the matching rate. There are, on the left, you can see analytic tools such as Atlas and Hades and Achilles. These are also softwares and tools that allows you to create your cohorts, define your cohorts, and run analytics on your cohorts. Next slide, please. Unlike Sentinel's C notes that Mike and Rob discussed, that Odyssey and OMOP is not friendly with SAS, which is very common in our fields. Instead, you have to use one of these platforms to host your database. SQL Server, SQLite, Oracle, and etc., as you see in this diagram. More and more new technologies are trying to adapt Odyssey or make it compatible with Odyssey, or Odyssey, as well as a community is trying to provide connectors, quote unquote, to connect your database in different technologies that is hosted, such as what you see in this slide, to the tools that are available in Odyssey, which that might be a good signal that Odyssey OMOP is becoming very popular, that all of these giant technology firms are trying to adapt Odyssey OMOP in their tools and solutions. Next slide, please. This was just until now just like an overview of OMOP common data models, and I would like to give you and walk you through an ongoing pilot projects that is happening through HDRN Canada. Next slide, please. In order to evaluate advantages and disadvantages of OMOP CDM for HDRN, Health Data Research Network Canada, we decided to design and create a very limited implementation of OMOP. As you see on the right, these are the organizations or data centers that participating in this exercise. Alberta Health Services, Alberta Sport Unit, Population Data, BC, Manitoba Centre for Health Policy, ICS, and CIHI are participating in this pilot study. In this study, the goal is to replicate an existing multi-province study that is already happening through traditional approach. And we wanted to replicate the same study and generate the same outcomes using OMOP approach, and to convert it to compare it and to be able to evaluate the advantages or disadvantages of OMOP for a network such as HDRN. We chose to use the replicating study to be the spinal muscular atrophy study, which is a very rare disease, SMA, for this purpose. Next slide, please. The reason that we chose this, because it was easy to replicate, and also it is very limited, and we wanted to able to, in a very short time, to fit it into our pilot study. We limited the outcome to socio-demographic, treatment patterns, and healthcare utilization. And study timeline, we limited to the availability of ICD-10-CA in the participating data centers. And for the purpose of the pilot, we excluded the physician visit diagnosis and fee codes, because mapping those to SNOMED CT itself is a huge undertaking. Next slide, please. Here you can see a timeline of the projects. I won't go through everything for the interest of the time, but as you see, we received funding from CDATO, the federal agency, in December 2023, and we started educating and learning the entire group of the projects by going through the online sources, courses, and etc., and starting developing the study design and implementation. We had one in-person workshop in Toronto, and we are planning to have another workshop later this summer to plan the replication of the analytics side. Next slide, please. Of course, we faced with a lot of challenges, but a lot of progress has happened. Open source softwares and data approval was one of the challenges. All of the sites, we got approval to participate to work, except one of the sites that couldn't get the approval. Only 2 sites were able so far to create one of the supported OMOP platform, MS SQL and SQLite. Others are working on it. 2 sites were able to run and assess the data quality. CIHI was very instrumental in mapping ICD-10-CA to SNOMED for us. Next slide. There are a lot of upfront major investment, of course, required for OMOP. There are a few examples here that we research in different organizations, how much they spend or resource the creation of the OMOP. We concluded that we would need a team of 3, a DBA, a data engineer, and a lead for each data center to be able to, in an expanded version, to create and run OMOP data. Next slide, please. This is a screenshot of Atlas, just to give you a sense of how it works. So it's an online tool, like a browser base. As you see in this slide, you can actually define your cohorts the same way that we are very familiar. So you identify the age limits, the gender, or any things that for entering to your cohorts, as we are very familiar. You define all of those. And then next slide, please. The next screenshot, this one shows you that once you create your cohorts, it actually creates a plain English version of your study design. which explain what are the inclusion-exclusion criteria and how the cohort is defined. As you see on the tabs on the gray tabs on the second row, it gives you the options to click on different type of coding programming to extract the code. And in the next slide, you can see an example of a code, for example. So MS SQL Server, Oracle, or whatever technology that your organization is leveraging, that is supported by OMOP, you can actually get the script automatically and run it to extract your data in your data center. Next slide. And this is my last slide. So opportunities that I can see by utilizing OMOP is, for example, Atlas can be available in one data center secure environment, and the project team can agree on one study and cohort definitions. And once they all agree, that one center can generate the codes and distribute the code to all other participating data centers. Another approach that I can think is generating a synthetic Canadian OMOP data to be created. There is a package actually supported by Odyssey. It's called OSIM, that allows you to actually create a simulated version of OMOP. And then imagine if we can do that and load that to a more accessible, publicly available environment with Atlas, the software, then researchers can go and run and create their own cohort definitions and generate the codes. And once they're happy with the cohort generation, then they can send the codes to the data centers who have agreements to work with them as a research project to actually generate the actual data cohorts on the real data. And with that, I'll pass it to Therese. Thank you.
Okay, good morning, everybody. So the title of my talk is Odyssey, which Mahmoud has just done a wonderful introduction to. And I'm going to talk about a new approach for analyzing observational studies using big data that came out of a lot of statistical research on how to do observational studies better that's been going on for the last 15 years. So next slide. Okay, so Odyssey is, as Mahmoud said, the Observational Health Data Science and Informatics program. It's multidisciplinary, multi-stakeholder, and it's a huge open science community that supports reproducible, systematized, open source analytic methods at scale. Next slide. So what the OMOP and Odyssey before them, what problem were they trying to solve? Well, the basic problem of variation across observational studies. In fact, John Ioannidis has famously published several papers. His big punchline is why most published research findings are false. So what are the problems? In this case, for example, JAMA, BMJ, 1 month apart. One study showed exposure to oral bisphosphonates increased the risk of esophageal cancer. BMJ had no association. Next slide. So another example, oral fluoroquinolones were associated with retinal detachment, and in JAMA, less than a year later, no association with retinal detachment. So the big problem, obviously, is reproducibility. Next slide. Okay, so what OMOP attempted to do starting about 2010 was to look into how bad is this problem. So they understood, as statisticians understand, that variability is related to sample size, power, that leads to bias. Huge flexibility for individual researchers to choose the study design, the definitions, tweak the outcomes, tweak the covariates, use different analytic methods, and possibly get different results. leading to that famous publish and perish syndrome among academics, of which we're all a little bit guilty, due to p-hacking. In other words, we publish the results that are significant. Next slide. So what they wanted to do was develop a data-driven, the eventual solution, the investigation was to see how bad is the problem, and the solution eventually, which we're seeing in modern day Odyssey, is how we can do better. So what they did that can only be done with modern high-speed computers, they ran experiments. So they had access to 10 huge high-quality databases with more than 200 million individuals, and they looked at 53 different treatment and outcome pairs. So some were classified treatment outcome as positive controls. In other words, the treatment was associated with the outcome. Some were negative controls. Treatment was known to be unrelated to the outcome. They looked at these 10 different data sources. They analyzed them with 14 different statistical methods: case control, prospective, retrospective, self-controlled, and numerous hundreds of different study designs. So choosing the exposure window, was it 30 days, was it 7 days? Choosing the look back window for covariates, choosing the number of covariates, choosing propensity-based strata, et cetera, et cetera. And they literally had something like 6,000 different pairs of relative rates that they could plot and look at. So next slide. This is just a schematic of what they did. And really the piece I'm trying to illustrate is at the bottom. So the treatments are across the top, the outcomes are across the side, and just taking you through the first column, which is ACE inhibitors. The red are the positive controls, the blue are the negative controls. So, and the white are the pairs for which they had no data. So ACE inhibitors are associated with angioedema. It's red, it reduces angioedema. ACE inhibitors, however, are not known to be associated with anemia, hip fracture, GI bleed. So they looked at these, 14 different treatments and numerous different outcomes. Next slide. So what did they do? So they computed a relative rate or a relative risk and a confidence interval for every different treatment outcome combination, for every different data source, for every statistical method, and every study design choice. And they literally had something like 6,000 different relative rates and confidence intervals. So for these 53 different treatment outcome pairs. So let's go to the next slide to just show you some of what they found. So this is a schematic of one statistical method. They used high dimensional propensity scores. The first 9 rows are the positive controls. You can't see the actual treatment and outcome, but just to say the first 9 are positive controls. These are pairs that are known to be associated. The true positives are green. So, and the false negatives are in yellow. So you can see that about a third of the studies where we know there's an association, a third of the study design data set pairs show not only no association, but no association. The 34 different treatment outcome pairs at the bottom are negative controls. So they should all be blue. They should all be true negative. And yet there's a number of them that are red that show positive, and they're really false positive. So it's not quite half, maybe a third are red. So this is already a little bit disconcerting. Next slide, please. They gleaned several different lessons. So lesson number 1, empirical performance. Most observational studies do not have the nominal operating characteristics. Actually, advance again. I think there's another piece to this. Yeah. Do not have the nominal operating characteristics they're supposed to have. So these are 34 negative controls, and we can look at the point estimates and we can look at the confidence interval. These are negative controls. So with a 95% confidence interval, 95% of these should cover a relative rate of 1.0, and yet half of them do not extend over the relative risk of 0.1. There's estimates on both sides of the null. It just shows huge variability in the observational methods. Next slide. And again, so here's another lesson, database heterogeneity. So this is where they held same analysis, same statistical analysis, run over different data sets. So you can see across a row, you'll see the point estimates for the 10 different data sets. The red show positive results, the green show negative results, and the ones in the middle are basically not significant. So interestingly, there is so much heterogeneity across data sets that statistically we would not even be able to validly pool these data. In addition, 20% of the time, the same data source had at least one positive and different data sets had one positive effect and one negative effect for exactly the same treatment pair. Lesson number 3. There's many lessons, but I'm just going to give you 3. Let's see, that's it. So this is now, we're going to look at exactly the same data with different study design choices. So different study designs means we use different covariates, we use different look back periods, different exposure periods, possibly tweaking the outcome a little bit. So again, huge variability. This is for example, do forward this one more slide. No, back. I guess it's not coming up, doesn't matter. No, back. Yeah. So one of those data points shows the results for one different study design. And for the same data, if you use different study designs, in other words, tweak the covariates, tweak the propensity strata, tweak the tweak the statistical method, this is the variability within one data set. And of course, we always like to choose the one that is statistically significant, but it just shows you the huge variability of the choices that a PI, a researcher, has using the same data set. So next slide. So what they decided to do was, I thought, extremely clever. Being statisticians, they started to look at the problem of p-hacking. In other words, researchers publishing studies only when they were significant. So here is one of the study results from the last slide. Sertraline, and GI bleed with a relative risk of 1.7, hugely significant when compared with the usual null distribution, which is a normal distribution. So they thought, okay, next slide, let's look at all of the negative controls. So these are all treatment outcome pairs within the depression. I think these were all treatments for depression. So these are all negative controls, and they should all fall within the, 95% of them should fall within the 95% band of the normal distribution. However, most of them don't. In other words, if you look along the x-axis, this is where the relative rates fall for negative controls. So about 55% of them are way out of the range of, well, where they should be. Let's say, if our statistical inference using a normal curve was correct. Next slide. Yeah, so 55%, so that slide. So then they got a very clever idea. They said, okay, instead of using a normal one distribution or a normal distribution, we are going to use an empirical null distribution. So no more normal distribution. You look along the bottom, you've got the relative rates for negative controls. Well, if you draw a distribution around them, that will be the empirical null distribution against which all studies run for this particular class of outcome treatments will be tested against. So no longer do we use the normal distribution, we now use the empirical null based on where the negative controls fall within this particular exercise. So next. I'm just going to be brief now. So they documented the problem really well. It's actually something we all know about, but they've documented it superbly to show that, even if you're a skeptic, no, the problem is real. So they developed, this is Legend, which is, they call it large-scale evidence generation and evaluation across a network of databases. So basically what they're saying is when you have a study question, and in this case, it was do first-line antihypertensives, are they which class of first-line antihypertensives, if any, are beneficial for cardiac outcomes? So the idea is go broad, engage numerous different scientists across the world with numerous different databases, develop for that problem a set of positive and negative controls, look at all the different drug classes. And in this case, it was all the different drug classes of antihypertensives, the thiazides, the ARBs, the ACE inhibitors, et cetera. Look at numerous different outcomes. So not just one, but look at heart attacks, AMI, heart failure, stroke, look at numerous different secondary outcomes, and look at, in this case, 50 different safety outcomes, and run everything, and most importantly, report all your findings regardless of positive or negative. Next slide. So what they found is, this is what is typically found in the observational research literature. In other words, if you look, they compile thousands of studies. 85% of studies have a p-value less than 0.05. Next slide. When you look at Legend, in other words, when they ran the study on 10 different classes of antihypertensives, 3 outcomes, 15 secondary, 48 safety outcomes, this is what they found. 85% of their outcomes were null. So I am just going to end. I'm going to fast forward the slides. That's the study, but so fast forward. Next slide. So basically what they are suggesting is, what Odyssey's vision is to collaborate, to do observational studies in a reproducible, systematized, open source manner at scale using negative controls, publishing all the findings. And they've had considerable success with this, they've published numerous different papers. And this is where I think ICES would like to go. So thank you very much.
Terrific. Thank you, Therese and Mahmoud and Robert and Mike for terrific presentations. We've gone about 5 minutes, a little bit more than that, for questions. There are a couple already in the chat, and so I think we'll go straight there. There are a couple questions actually about indigenous data. One was about non-insured health benefits data, and the other was more really around OCAP principles and how those are managed in these types of studies. So maybe Mike or Robert might just talk about CNODES and its approach to indigenous data in Canada.
Sure, if you like, Robert, I can start and then turn it over to you. So where the Indigenous non-insured health benefits data are concerned, I'm speaking for Ontario at the moment, We don't actually have access to those claim data. Those are federal claim data. And in Ontario, we only have access to the Ontario drug benefit data. Unfortunately, we can't study those claims, those exposures in our studies. That's not the case, however, in other provinces where the teams have access to all drugs, all people data sets, and in essence, data sets that are agnostic to the funder. And these include both the public plans at the provincial level, the federal level, private insurers, and out-of-pocket purchases. All of those data are available to the researchers in those settings. So I guess at a high level, I would say that those data are included in our studies in the provinces where we have access to them, but not separately from all of the other payers in the data set. So that's how we've handled it. We've not specifically teased out the non-insured health benefit data, but they are accessible to researchers in those provinces.
Great. Okay, thank you. Another question regarding data sources in Canada versus the US, why they weren't kept the same for Canada and the US. So maybe just talk a little bit about, I guess, the comparability of data between Canada and the US in the FDA Sentinel CNOS model.
So in the specific application that I think this question is referring to, the study that we did looking at thrombosis in patients with COVID, they involved a number of data partners in the US, only some of which had access to PCR lab data for COVID diagnosis. The remainder of those centers, unfortunately, had to use diagnosis codes. And that was the main driver of the heterogeneity between the US and Canadian sites. Whereas we had provincial registries for PCR lab data in the provinces in Canada that participated, that was not the case in the US. And so unfortunately, they were forced to use a combination of multiple data sources for defining their COVID cohorts.
Okay, maybe I'll take the moderator's prerogative here and just ask the final question that we have time for. So I'm just imagining a researcher out there who's interested in doing research across Canadian provinces or different countries, and we've seen some nice examples of that this morning, but who doesn't have experience of working with common data models, but also doesn't have experience of undertaking multi-jurisdictional research in across different data centers. You know, all of you have participated both in research using common data models and research where you use common analytic protocols where the data wasn't standardized. Now, you have a lot of experience, all of you, but from your point of view, what would be your advice to a researcher out there embarking on this path and thinking about, should I be trying to work with a common data model across those centers if I have the opportunity to, or should I be trying to work with the de novo data and a common analytic protocol approach?
Maybe I'll just start really quickly. I think research is a team sport. You can't do it alone. I don't think any of us, to say this person doesn't have experience, none of us really have experience with common data models and multi-jurisdictional research. I do think it's the future, though. So I think if we're to go in that direction, we need support for this. I think the days of the one data set, one study design, I mean, we already know that there's issues with that. So I think this is the way of the future.
Robert, Mike, Mahmoud, anything to add?
Well, I'll just say that certainly there are research questions that are well suited to the common data models, at least in our limited experience. There may be research questions that either for whatever reason we don't have the data sources coded in common data models at the moment. So we'll have to be relegated to a protocol-based approach. But I agree with Therese that I think increasingly we will want to use our common data model tables in our CNODES work. We've demonstrated that we can do so more quickly, more efficiently. And so I think to the extent that we can move to using them on a more consistent basis in the future, we certainly will.
Robert, do you want to add to that?
I'll just add that there's a lot of open source learning material about both of the common data models that we talked about today, in particular Odyssey online. And I won't minimize the learning curve, having worked at a high level with these common data models, but not been in the weeds with hands-on analytics. The learning curve is not small, but there is a lot of openly available training and tutorial material that people can get up to speed with. But it will take some time and effort.
And if I may just quickly add, perhaps networks like CNODE and HDRN is the right place to start to discuss whether this particular research is well suited for common data model or not.
Mm-hmm.
Great, thank you all. And I'll just give a plug to HDRN, Health Data Research Network Canada. There is a session this afternoon that describes it. Also, there is a free online webinar series on distributed analysis that is recorded, and if people want to learn more about it, they can do so. So I'll just take this opportunity to thank our 4 terrific panelists. I think that was a really great overview of common data models and opportunities for multi-jurisdictional research. So with that, we'll go to a break now for 15 minutes, and we'll all come back at 11:30 for the spotlight session. So I encourage you to join one or more of the spotlight sessions at 11:30. All right, bye for now.